So this is the outline. So we will introduce what is a capacitor and calculating the capacitance of different structures. Actually, you already know what is capacitor. It can be as simple as a parallel plate like that, and then you put some charge in opposite sign on them, and then it forms a capacitor. Okay, so capacitor in parallel and series, very simple, and then energy stored in the electric field within the capacitor, and also the capacitor with a dielectric, a little bit more complicated, but still fine. And actually, we need to use a Gaussian law to derive those equations, or make some modification to the Gaussian law. Okay, here is the definition of a capacitor. So a capacitor consists of two isolated conductors, the plate with charges Q plus Q and negative Q. So its capacitance is derived from this expression, Q equals CV. Q equals CV. So this is the most useful formula for capacitor. Actually, I still using it in my research recently. So it is a very useful expression, I say. And yeah, so this is nothing special. Q is the charge, SI unit is Coulomb, C is the capacitance. Is the capacitance. So if you would like to regard it as a definition, you can write it as E equals QV. So we already know what is Q, what is V. V is the potential difference between these two plates. Potential difference. So actually, what you need to remember is the SI unit. SI unit of V. The SI unit is Farad. Actually, name it after the Faraday. You learn the Faraday's law in chapter 30. Chapter 30. So F. So don't try to write it as something like C over V, something like that. Although it is correct, but Farad is the general SI unit we use for the capacitance rather than using C over V, something like that. Okay, so here you can see the structure, nothing special. And here it says, as the field line show, the electric field due to the charge plate is uniform in the central region between the plates. The field is not uniform at the edge of the plate as indicated by the fringing of the field line there, fringing. So in Chinese, it is called 边际. So fringing mean that part. So at least it says inside the capacitance, the electric field is approximately uniform. In previous chapter, what you learn is that if the parallel plate is infinitely large, then it will generate uniform E field between the plate, or at least even if one plate, which is infinitely large, it will generate E field like that. So now, of course, a practical capacitor cannot be infinitely large, but at least inside the capacitor, or at least in the inner part, the E field are quite uniform. For the edge stuff, it is a bit weaker, and even for the outside part, it might be something strange. It's something like the E field line of a dipole, something like that. Don't care the outside. For a capacitor, usually we only care the inside part. So yeah, even though we did not have the infinitely large assumption, then if we just consider that part, the E field is approximately uniform. Yeah. So the next, we will see there is an experiment about this capacitor. So yeah. So here, when a circuit with a battery and open switch, a battery, open switch, and uncharged capacitor is complete by closing the switch. So this is a battery, this is a switch, and this is the parallel plate as a capacitor. So drawing this is time consuming, so we will have is according electrical symbol. So the battery is like a one line with a short line. So to specify this is a battery, and the long lines means it is a positive edge, and this is a negative edge. And the switch is nothing like this, with two dots and a line here. So it is a switch, which means that it can be closed like this, and it can be open like that. So this is a switch. But usually we will write it like a open state, because if we draw it like this, if you don't pay attention, you will miss this point, and then you will just miss the switch there. So usually when we try to draw the switch, we will draw it like this. And for capacitor, you will only draw a parallel line, two parallel lines to specify the capacitor. And of course, for the battery and the capacitor, the two lines are of different length for the battery, but for the capacitor, the two lines will be should have the equal length. Okay, so this is a circuit connecting the battery, capacitor, and the switch together. So of course, this is a wire. And yeah, the battery maintains a potential difference V between its terminals. So suppose this V doesn't change. So the terminal of the high potential is labeled positive, and it's often called positive terminal. And the terminal of the lower blah blah blah. Okay. Wait. So okay. So yeah, so it's just like if you just put a battery here with a potential difference V, and this is the capacitance C. And then if you just close the switch, then there will be some charge at this side, positive charge at the left side, and the negative charge on the right side, because this is a positive, this is positive, this is negative, so this is negative, and this is Q, this is plus Q, this is negative Q on the right side, the right plate. And it will satisfy Q equals CV. Q equals CV. Okay, so nothing special. So here, let's consider the E field inside the capacitance, the capacitor. So, so to relay the electric field between the plate of a capacitor to the charge Q on either side, we shall use Gaussian law. So if you still remember, the Gaussian law is written like this: the potential difference between the plate of a capacitor is related to the field by this expression. So if you still remember, so this is from chapter 23. This is from chapter 24. We just finished it in the last chapter. So yeah, so we make use of these two expressions. And yeah, and of course, we already know that the E field is uniform. The E field is uniform at the inside part, and the E field is actually parallel to the path. So in this case, we will consider the initial point at the negative plate, and the final point at the positive plate. And then it is perpendicular to the plate. So in that case, you see for this part, ds is pointing upward. ds is pointing upward because you move from I to F, pointing upward. And the E field should be from the positive plate to the negative plate, which means E is pointing downward. E is pointing downward. E is pointing downward here. So E dot ds is negative. E dot ds is negative E ds, like this. So this negative sign and this negative sign will cancel each other, and then we only take V to be the difference between Vf and Vi. So V here, and then these two negative sign cancels. So it becomes EDS here, and then we integrate from the negative plate to the positive plate. So we have put negative plate and plus here, like that. So we get this expression, and then okay. So now we can apply the Gauss law. The Gauss law will be like that: E dot dA epsilon naught Q enclosed. So here we consider the Gauss law to be this red dotted box like this. So this side is inside the capacitor plate, so there is no E field. There is no E field crossing through this surface. And so as this one, the E field is parallel. It's actually perpendicular to the dA. To the dA for this side, for the dA for this side is perpendicular to E. So there is no contribution either for this surface and this surface. No E field for this for the upper surface either, because there's no E field. So the only E dot dA will contribute is the lower surface. So here we assume the surface area is capital A, and then E field is uniform. So it is nothing but E times A. So we have E times A here times epsilon naught. So this is the phi. And then Q is the total charge enclosed by the capacitance. Enclosed by the Gaussian surface, which is all the charge stored at the capacitor on one plate, on the positive plate. Okay, so this is the Gauss law, and then we make use of this expression. So E is a constant. So we can just factor it out, and then we integrating ds from negative to positive, which means it is nothing but the distance between the two plates, which we define it as d. Okay, so V, the potential difference between the parallel plate is nothing but E times D. So we have E times D equals V, and also we have this expression for the E, so that we can eliminate the E like that, or we can just plug in something else. So we can see Q equals CV, which is the definition of the capacitor, so that Q equals CV, so that we plug CV into here to get this one, and then epsilon naught EA, we can have this one to be E equals V over D. And then we put this one here. So we have V over D here. And we find that V and V can be cancelled. V and V can be cancelled. So which means that C equals epsilon naught A over D. So this is the expression for the capacitance of a parallel plate capacitor. So this is C equals epsilon naught A over D. And it says epsilon naught is a constant, 8.85 times 10 to minus 12. And this is A. This A is the surface area of the capacitor. and D is the distance between the two plates, which means if you want to have a large capacitance, you need to increase the surface area, increase the dimension of the capacitor. However, you can also making the plate as close as possible, as close as possible. Of course, they can't touch each other. Otherwise, the positive charge and negative charge will cancel. You need to hold the capacitor, the parallel plate at a small distance to make the capacitance to be large. Okay. So next is a cylindrical capacitor. Cylindrical capacitor, 圆柱电容啊，圆柱电容。So this figure only shows the cross-section area. So actually it is like this. It is like this. Like this. Yeah. So this is the outer plate. This is the inner plate. So this is the outer plate, the inner plate. Okay. So in cross-section, a cylindrical capacitor of length L formed by two coaxial cylinders. Coaxial means 同轴啊，同轴。Co means 同嘛 and axial means axis. So coaxial, which means that this is a cylinder and this is another cylinder. They have the same axle, which means that the center point. So this is the axle, or the center point of the circle, of the cross-section circle, and then you connecting them together, which means that for this cross-section, this circle and this circle has the same center point, which means that they are coaxial, and then the axes are parallel to each other. Okay, so formed by two coaxial cylinders of radius A and B, radius A and B. So the smaller one has a radius A and the larger one has a radius of B. So we assume that L is much larger than B. L, so this is L, the length is much larger than B, which is the outer radius. So we can neglect the fringing of the electric field that occurs at the end of the cylinder. Each plate contains a charge of magnitude Q. So here, charge and the field magnitude E is related as follows. Still, we use the Gaussian law. E dot dA times epsilon naught equals Q enclosed. Okay, so here, as you can see, this is a actually this is something like parallel plate, but this is a curvy parallel plate. This is a circle, and this is another circle, and they are in some sense parallel to each other. Okay, so actually there is some symmetric in this shape, which means that this is a positive plate, this is a negative plate, and you can imagine the E field should be in radial direction. Radial direction means like this, like that. These are all radial direction. So they should be all parallel to the R axis. There shouldn't be any E component in this direction, in theta direction, something like that. There shouldn't be any component like that. Okay, so here still, well, so E, I think. So here we concern the surface area is like this. The surface, the Gaussian surface is this one. And of course, dA should be pointing outward. dA should be pointing outward. And And E should point to the same direction, which means E dot dA is nothing but E dA. Okay, so we have E times A here. We assume the E field is uniform over this Gaussian surface. So the left side is nothing but E0 times EA, epsilon 0 times EDA, times EA, like this. And Q is actually the charge inside, which is Q. So the surface area is nothing but the 2 pi r, which is 2 pi r, which is the circumference of the circle, and then times the height. Because if you try to cut it out like this and then expand it, it is a rectangle. So the width is 2 pi r, and then the height is L. So this is the surface area. So we get an expression like this. Then for the V, we still use this expression, but the E is not uniform. Actually, E equals, let's see, E equals from this one, we can see, we just put this part and this part to the left side. So we have Q over 2 pi epsilon naught L R, something like that. And then we put it here. So Q over 2 pi epsilon naught L is here. And yeah, like this. And actually, we rather than integrating from actually we need to integrating from the negative plate to the positive plate, which means that we actually going in this direction. So E dot ds, we should have a negative sign here. Because we go from this side to that side. So from B to A. So we have a negative sign here. So here we have Q over 2 pi epsilon naught L, like this. And then 1 over R is related to dr. So we still keep this term inside, and then we just integrate it. So this is 1 over R, and then we take the integration, take the antiderivative, which is nothing but log of R, which is nothing but log of R evaluated from B to A. And then with this negative sign, so it is like, so this is like log of A over B, which means this is log A minus log B, which is log A over B. And with this negative sign, we put it there so that we reverse it. So we finally have log B over A. And and this is V. So finally, we would like to find C equals Q over V. Which means that we just move this V to the right side and move all this term to the left side. So this is Q over V equals C. And finally, C will be 2 pi epsilon naught L, which is this term, and log B over A is actually this one. So we finally get the expression of the capacitor J of a cylindrical capacitor like this. So pretty much like that. And so next is we talk about a spherical capacitor. So although the cross section is the same as before, but actually it is something like I don't know how to draw this one. Actually, a sphere 球体球形电容 So the inner plate is actually a sphere, and the outer plate is also a sphere with the same center. So in the cross section, it's actually the same, but of course it is different. So if you're interested, you can try to derive it by yourself. It is not so difficult. Actually, you can try to derive it. I think two years ago, I have asked it in midterm exam. So if you're interested, you can try to derive it by yourself. Yeah. So this is the expression for the variable capacitor, and here we have a so-called isolated sphere, which means if we take B tends to infinity, which means the outer plate doesn't exist, then A is the R. So we only have a single sphere, with the radius R. Then the capacitance is like this one. This one, if we pick B tends to infinity, which is like C equals 4 pi epsilon naught A, and then we divided B here, so we have 1 minus A over B, and B tends to infinity, so it's changed to 0. Like this. So, and we take A to be capital R. A to be capital R. So this expression like this, is like this. So here is a quick checkpoint. So it asks for the capacitor charged by the same battery. Does the charge stored by the capacitor increase, decrease, or remain the same in each of the following situations? So a plate separation of a parallel plate capacitor is increased. So if you still remember, C equals epsilon naught A over B. So if you increase the separation, which means increase D, then C will decrease. Decrease. Okay. So for the next one, the radius of the inner cylinder of a cylindrical capacitor is increased. So if you still remember, it is 2 pi epsilon naught L over log V over A. So the radius of the inner cylinder of the capacitor increased, which means A increased. A increased, which means that this term decreased. So this will decrease. Sorry. A increase, the term decrease, and then whole term increase. Yeah, increase. Increases. Yeah. And then for the final one, the radius of the outer sphere, C equals 4 pi epsilon naught A B B minus A. Or we can make it like 1 over A minus 1 over B, like this. We just divided AB on both the denominator and the numerator. So if we try to increase the outer sphere is B, increase the outer sphere. This one increase. So this one decrease. This one decrease. So this one increase. So the whole term decreases. Okay, decreases like that. Okay, So let's see a sample problem. So switch S is closed to connect the uncharged capacitor of capacitance C to the battery of the potential difference V. So the lower capacitor plate has a thickness L equals 0.5 centimeter. The phase are A, blah, blah, blah. And it consists of copper, in which the density of the conduction electrons is N equals blah, 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 electrons per meter cube. For what depth D within the plate must electron move to the plate face as the capacitor becomes uncharged. So actually, what I told you is for the conductor, we will assume all the charge will be on the surface, but actually, the density of the electrons is finite, although it is really large. But actually it's finite. So there is still a thickness. So the thickness of this plate, there is still a thickness, although it's very small. And let's see how we can calculate it. So the first step is use the Q equals CV. So C is 0.25 times 10 to minus 6, and then V is 12. So this number is 3 times 10 to minus 6 coulomb. Okay, this is the charge. This is the charge at the both the top plate and the bottom plate. And then N. Capital N. Capital N is the number of electrons. Which is like the charge divided by the elementary charge, 1.6 times 10 to minus 19. So this is a charge, and each electron will contribute 1.6 times 10 to minus 19 coulomb of charge. So let's see how many electrons must be stored at the bottom plate. So this is 1.87 times 10 to the 13 electrons. Okay, so next, we should have this height to be B, and then we have the surface area A. So this is the volume. The volume will be A times B. So this is the volume density. So N times AB will be the total number of electrons, which means that D equals capital N over NA. So which is 1.87 times 10 to the 13th power over 8.49 times 10 to the 28th power times A is 2.2 times 10 to minus 4. Actually, this L is not useful for this problem. And finally, you can see that 1.1 times 10 to minus 12 meter, which is like 1.1 picometer. So which is very big. So next, let's see the capacitance in parallel and in series. So I think most of you are ECE students, so you have learned the circuit analysis. So you know how to calculate parallel capacitor, series capacitor. So actually, if you are not ECE student, then just just explain it quickly. It is not difficult, only some algebraic calculation. So for parallel capacitance, in Chinese called 并联. So 并联 parallel is like we have C1, C2, C3. So we connect all the top plate together, and also we connect all the bottom plate together. So this is called parallel. And yeah, and if we just provide a voltage difference here, in that case, they will share the potential difference, and then they might have a different amount of charge. They might have different amount of charge with a different capacitance. So in that case, we will try to find the equivalent capacitance, which is like if we just remove this part and then put this CEQ here, and then the voltage and the charge look exactly the same like this one, which means that Q, small q equals to Q1, Q2, Q3. We add them together. So we have Q equals Q1 plus Q2 plus Q3. And we can substitute this term here. So we get C1V plus C2V plus C3V. And then we can just factor out these, so we get C1, C2, C3. And for this one, we can simply have Q equals CEQ times V. Comparing this one with this one, we should get CEQ should be C1 plus C2 plus C3. So the parallel capacitance is nothing but to add all the capacitance together. And if we have number of n, then we just add all of them together. And for series capacitor, we like to connecting them back to back, which is like connecting the bottom pair of the first one to the top pair of the second one, connecting the bottom pair of the second one to the top pair of the third one, so on and so forth. So it is like series, in Chinese called 串联. So in that case, because before we apply the battery, which is like this point should be neutral. Electrically neutral. There is no charge at this node or at this node. So in that case, we should have negative Q plus Q, so that the net charge of this node is neutral, and so as this one. So finally, we can see that for every capacitor, even though the capacitance are different for series capacitor, then the charge should be the same, because this center node should be electrically neutral. In that case, we see that the charge are shared by different capacitors. For previous one, the sharing variable is the voltage difference. So this is the difference between parallel and series. So we have a Q equals C1V1, Q equals C2V2, Q equals C3V3. And here we'll use something called the KVL, the Kirchhoff current law, which is like when you go from this point, the voltage difference go up by V, and then drop by V1, drop by V2, drop by V3. Go up by V, and then go down by V1, V2, V3. So in that case, V should be equals to V1 plus V2 plus V3, like that. Okay, so we can just plug in these three quantity here. So we have Q as the common factor. So we put it in the front. We have 1 over C1 plus 1 over C2, 1 over C3 inside. And likewise, for this equivalent, we just remove these three capacitor in series and replace it by CEQ. So this one, we can also write it as Q equals CEQ V, like that. So in that case, or we can write it like V equals Q over CEQ, like that. So comparing this one with this one, for make it view, you can just put it here, 1 over CEQ, something like that. So you can see more clearly, Q times 1 over CEQ equals V. Comparing with this one, we have V equals Q times this term. So 1 over CEQ should be this term. 1 over CEQ should be 1 over C1 plus 1 over C2 plus 1 over C3. So we just put it upside down. So CEQ equals 1 over the whole term here, like that. So generally, if you have a n capacitor in series, so you take the reciprocal of the capacitance and then you add them together and then take the reciprocal again to get the equivalent capacitance of the series capacitance. Yeah, so more or less like this. This is a parallel capacitor. You just add them together. For the series capacitance, take the reciprocal, add them together, and take the reciprocal again. Okay, so next, this is about the energy stored in the electric field. Energy stored in the electric field. So yeah, so this is the derivation. So we have U. U is the du integration. And then du equals V dq V dq. In the last chapter, U equals VQ or QV. And yeah, here we also consider the infinitely small Chap will contribute some potential energy like this, and then you integrate them together because we actually need to consider like that way. So we integrate from 0 to Q, which means that if we have a capacitor, originally there is no charge, and then we try to put some dq here, and then minus dq there, and then you need some energy to serve this, and then you put another part dq, negative dq, with the existence of the first part, and then you do it all the way up to Q. So the integration is something like that. Okay, and as much as we have Q here, so we make it Q prime for the dummy variable. And V equals Q prime over C. V equals Q prime over C. Because as much as you try to put some of the charge here, then the potential difference between the plate will increase gradually. So B equals Q prime over C, and then you integrate it, integrating the Q prime from 0 to Q. So this is pretty easy, which is something like integrating x dx. Something like it, which is 1/2 x squared from 0 to x. something like that. So you have 1/2 x squared. So you have something like that, q squared over 2c. And usually what we will use more frequently is actually 1/2 cv squared by substituting q equals cv. Q equals cv. So we will have 2c, and then we have a c squared v squared, so that you can cancel one of the c, becomes 1/2 cv squared. So for the circuit point of view, we seldom consider the charge, but this is a physics textbook. It's usually use the Q, But in circuit theory, we usually use the lumped circuit element like the current, voltage, or in this course we call it potential difference. Okay, so this is the energy stored in a parallel capacitor or stored in a capacitor. And here it mentioned about the energy per unit volume. Energy per unit volume. It is not so useful here, but we will use it in chapter 33, mentioning the electromagnetic wave, the EM wave. And at that time, we will use this expression. So let's see how we can derive it. So the total energy is U. So the energy per unit volume is like the U divided by the volume. So for simplicity, we consider the parallel plate, and we have the cross-section area A, and the distance between the plate is D. And we pretty much assume the E field is uniform, so that the energy stored there are also uniform. So it is pretty much like U over A times D. So U is 1/2 CV squared over A times D, like this. So we have 2AD and then V squared. V squared, yeah, like this. V squared. Maybe we can directly put in. If you still remember, V equals ED. V equals ED. Just by this one, E dot ds from negative to positive. If it is uniform, it is nothing but E times the distance. E times the distance. So we have this. We have this expression, and also for the parallel plate capacitor, we have C equals epsilon naught A over D. So we have C. C is epsilon naught A over D, and then times V equals E squared D, which is E squared D squared, like that. So we plug in these two into here. So we can find that D and D can be cancelled. D and D can be cancelled. A and A can also be cancelled. So it turns out to be 1/2 epsilon naught E squared. So it is also correct for other structure, although the derivation won't be so easy as this. We only need some algebraic calculation to come up with this one. But yeah, for general derivation of this one, you only need the complicated integration. So we do not provide the derivation here. Okay, so let's stop here today.